My name is Ying Tong, and I'm actually Weiji's colleague. And I think I wanted to follow his talk because the subject of this talk, voting schemes, is also marginally related to preserving the privacy of your computation. And voting schemes are the latest development in zero-knowledge proofs. They're a way to make the zero-knowledge prover very efficient, um, both in terms of space and time complexity. So I want to start off by, motivating this talk. We're interested in voting schemes because they allow us to achieve a primitive known as incrementally verifiable computation. And how you can understand incrementally verifiable computation is by taking a large monolithic computation and breaking it down into many repeating units, such that each step is now an incremental unit of work. And this is useful if, for example, you're memory constrained and you simply cannot hold the whole circuit F. So incrementally verifiable computation allows us to compute a long and complex chain of computations, but using a very constrained resources. This is useful in a bunch of applications. So for example, Meetup protocol uses IVC to provide a constant size proof of the validity of the whole blockchain. So to convince yourself that the whole history of the blockchain of n blocks is valid, you need only verify a single proof. To be clear, Meetup protocol still requires full nodes and archive nodes like ChainStack provides. But the point is, if you're a light client and you want a higher assurance that your archive node is serving you the correct data, then IVC will help you do that. Some other applications are, for example, RISC-0, which proves the correctness of the execution of a RISC-V program. Now, these RISC-V programs, the traces can get very large, and so RISC-0 makes the prover manageable by breaking down the trace into iterative steps. And lastly, some people have been applying IVC to something called ZK machine learning, whereby you have a neural net with a very repetitive structure. Basically you can break it down into clean, self-contained layers. So we're interested in voting schemes because they allow us to achieve IVC using the smallest recursion threshold, meaning that at each step, the overhead that we need to pay to verify the previous step is very small. Also, you can ask questions whenever. I hope I've motivated folding schemes sufficiently. And the rest of this talk will basically introduce the mechanisms behind folding schemes. And as I said, this is where a lot of research interest is in the world of zero-knowledge proofs currently. So I hope that after this talk, you'll feel comfortable looking at some of the literature that's come out. Oh, whoops, ignore that. So as we discussed, a folding scheme is a way to instantiate incrementally verifiable computation. So if we start out with some NP relation, like a RISC-V, the correctness of a RISC-V program execution, or the validity of a chain of blocks, we can basically encode that. We can build a folding scheme that checks this NP relation. And yes, yeah, the complexity NP relation. And then we do some transform to make this folding scheme non-interactive. And this is crucial for it to be actually usable in the real world. In the sense that you, the prover, should be able to do all this work offline by yourself and not rely on some response from the verifier. And at the very end of this chain of incremental work, we can attach a ZK snark. And what this does is it introduces privacy, zero knowledgeness, and also it reduces the proof size, makes it succinct. So this is just the overview, and I hope each of these things will become clearer as we go into it. But so first of all, NP relation. This is the complexity theory NP relation, whereby you have a language consisting of instances X, such that there exists some satisfying witness for XW in the relation R. So to make it concrete, let's say we want L to be the set of composite numbers, so the numbers that are not prime. So our relation R would check that there's some witness W that is a factor of X. So X is a composite number. So this relation R, we can encode in an arithmetic circuit. And this is what, So this is what is known as arithmetization in the zero knowledge world. So one popular arithmetization is called the rank 1 constraint system. And this is basically a very lightweight way to capture NP problems. So we're not going to go into the details of R1CS. You can treat it as a black box. But maybe the most helpful illustration is the one on your left, whereby your NP relation is represented as a series of addition and multiplication gates, each with a Fanon2 inputs. So we compile this arithmetic circuit to a problem that we can check very efficiently using a few probabilistic checks. So that's the whole point of arithmetization, is to take your NP relation and encode it in such a way that checking its correctness becomes very efficient. Of course, this introduces an element of probabilistic correctness. So you can make some very efficient algebraic checks that will convince you with high probability of the correctness of this relation. So now, from this NP relation, we can now build up what's known as a folding scheme. So a folding scheme is a way to combine the correctness check of two NP relations into the correctness check of a single accumulated NP relation. Okay, so, and this only makes sense if, okay, yeah, so the guarantee that I'm giving here is that this new folded instance is satisfiable if and only if the two original instances are satisfiable. So basically, you don't lose any correctness by folding. That's the guarantee of a folding scheme.
Is it a probabilistic guarantee or like
Probabilistic guarantee, yes. And furthermore, this folding step is only interesting if it's cheaper for you to verify a single witness. If it's cheaper for you to do one fold and one verification compared to just doing two verifications as you would have usually done. Yeah, so crucially, this folding step has to be cheaper than one verification, right? So we're not going to go into the details of how the R1CS instances are combined to form a new one. But I think what's worth noting is that the folding step basically introduces some kind of error or slack terms. And yeah, it alters actually the original relation such that if you had two strict R1CS instances, you end up with a folded instance that is relaxed, meaning that has some error terms introduced to it. And the job of the folding step is to check that these error terms were correctly derived. So you can't put any error you want. You have to derive the error specifically using some cross terms generated by the strict R1CS instances. So So the reason why the folding step is so efficient is because it only has to read, let me see. It only has to read the instance, which is a succinct representation of the witness. So in a circuit, your witness assignment can be length n, but the folding step only has to interact with a constant size commitment to your witness. And this is secure if the commitment scheme that you used is binding, meaning that given a single commitment, I cannot find two witnesses that both reproduce it. But I'm gonna skip over the details of how the commitment scheme works because it involves elliptic curve cryptography. But the high-level properties that are important are that, first of all, the commitment is constant size, even if the witness to which it commits is length n. Secondly, the commitment is binding, which means that it holds you to that witness and you cannot convince someone else that it actually commits to another witness. And thirdly, it's important for the folding step is that this commitment scheme has to be additively homomorphic. So if you recall from Weijia's talk, what this means is that adding two commitments is equivalent to committing to the sum of the two original witnesses.
How long is a commitment in practice?
How long is a commitment in practice? It is. In terms of bytes.
Yeah, roughly.
It's like 64 bytes, I think. Yeah. So, yeah, in the systems that we use, the witness is a bunch of field elements in a finite field, mod P. P is usually 256 bits. And a commitment is a group element which consists of the X and Y coordinates, two field elements. So you have like 256 bits, 256 bits.
So half kilobyte.
So that's like 64. I can't do math, but yeah. 256 bits is 32 bytes, so 64 bytes. Yeah, 64 bytes. Okay. Yeah.
I just want to get a sense of the improvement. So you said, because I know that verification itself is efficient itself. So if we compare the before folding and after folding, before folding there's a two verification, and after folding is one folding and one verification. So do we have an analysis about like folding is like constant time and verification is like log time? Can we say that like so the improvement is like I do improve the operation from log time to constant time? Is the idea?
Oh, that's a very good question. So you are correct in that for a ZK snark, the verification is succinct. So the verifier of a ZK snark the fastest known verifier is constant time, right? There's like log n times. So the thing is though, what we're folding is not a ZK snark. We're folding an NP relation. So to verify that NP relation is actually linear time. Yeah. So yeah, you're saving one linear time thing and replacing it with a folding step, which is constant size.
Okay.
Yeah.
This basically reduces the approval time.
Yeah, that is correct. This reduces the prover time. So in classical IVC, each recursive step would have had to fully verify a snark proof, meaning that at each recursive step, the prover would have had to produce a snark proof. Whereas in folding, as we saw earlier, we're not folding a snark. So the prover doesn't need to do anything to his relation. The only thing the prover needs to do is compute the commitment, as we discussed. So yeah, why this folding scheme is appealing is that it reduces proving time. Yeah. The verifier time, so, So the thing about this IVC is that basically each recursive step is a prover and also a verifier in the sense that each step attests to the validity of the previous step. So it's kind of like a verifier. But at the same time, at each step, we produce a proof that we send to the next step. So it's kind of a prover. So the point of IVC is that you can verify the whole chain of computation at the very end in constant time by taking just the final proof, because that proof attests to the validity of all proofs before it. So to answer your question, if the verifier's efficiency has changed, naively, the folding scheme verifier is linear time, as we discussed. So naively, we would have to do, at the very end, a linear time check. So maybe that's okay if you amortize it across n steps at least. But if you want to avoid that linear time check, you can put the proof at the very end into a ZK snark. And we know that the verifier for a ZK snark is succinct. Yeah. So in practice, that's how it's done, actually. So you fold cheaply as many times as you want, and then do one sort of expensive proving operation in order to produce a succinct proof that you can send to anyone to cheaply verify. Yeah. So again, when we come back to the use cases, for example, like a light client running on a mobile phone, they can verify the validity of n blocks, and it takes you like it won't take you forever to generate that proof, you know, because you folded. Yeah. So there are some technicalities here, in the sense that at each folding step, we need to introduce some randomness that is not controlled by the prover. And this randomness is what's used to linearly combine the two instances into the folded instance. So if the prover knew this, if the prover could pick this randomness, then they could basically pick some pathological combination of input instances that individually are not satisfying, but produce a folded instance that is satisfying. So the prover cannot choose this randomness. So now, one way to get this randomness is to ask the verifier to send it to you. But in the real world, that will require the verifier to be online at every step, which is too annoying. And the only way to realize this is to make it non-interactive. So the intuition here is that the prover derives this randomness from the very inputs that he's trying to linearly combine. And so basically, in order to change the randomness, he has to change the inputs. So he can't just choose any input he wants. He has to do a lot of work to brute force the pathological inputs that will give that desired randomness. So usually this amounts to breaking the security of some hash function.
I guess you can make it extra expensive, like by repeating the hashes.
Yeah. I think this hash function is essential to the security of the folding scheme. And actually, it's the point of quite some debate when people are trying to make security proofs, because this hash function has to be actually represented inside the folding step, so inside a shallow depth circuit. Yeah. So, but yeah, this hash function is crucial. And this sort of transform from an interactive protocol to a non-interactive protocol, and at the same time preserving the security of the randomness, it's called the Fiat-Shamir transform, and it's used everywhere in zero-knowledge proofs. So finally, now that we have a usable non-interactive folding scheme, we're ready to instantiate the primitive we wanted, which is incrementally verifiable computation. So as we saw before, the sort of classic IVC actually works with a snark. So someone was saying just now, isn't the snark verifier succinct? Which it is. And that's why you can fit a snark verifier into each step of the IVC. And this is how IVC was classically instantiated. And the problem with this, as we discussed just now, is that this snark verifier now expects a snark proof at each step. So it expects you, the prover, to have computed that proof at each step. And this is expensive most of the time. It involves doing a lot of FFTs and a lot of multi-exponentiations. And so the point of folding scheme is that we replace the snark verifier with a folding verifier. And the folding verifier has way fewer responsibilities. It just checks pretty much a hash. It checks a linear combination. That is about it. And so it has fewer expectations of the prover. It just wants from the prover some commitments, constant size commitments, and some claimed hashes.
Are those hashes from the fiat Chami or?
Yes, exactly. So the verifier must check that the prover's claimed randomness was in fact derived from its claimed instances. So yeah, we've now reduced the recursive threshold significantly, which speeds up each step of our IVC, which is very nice. And yeah, if you want to really get into the weeds of this, what I've been describing today is a protocol called NOVA. It's by some researchers at Microsoft. So you can look that up if you're interested.
Does this chain have to be linear, or could you also build something that branches?
Yeah, so the question was, must it always be a linked list kind of structure, or can we have a DAG, right? So I think incrementally verifiable computation, which was introduced in 2008, was linear. And then in 2010, some people generalized it to a primitive called proof-carrying data, which allows for a DAG. Yeah. But, you know, even on the NOVA protocol, people are basically introducing useful modifications. So for example, what if instead of a single predicate F, at each step you could choose one out of L predefined predicates? So why you might want that, for example, you're trying to represent a state machine and each predicate is an opcode. And they call that non-uniform IVC because even though you're choosing from a predefined list, at each step you can do something, a different step from that list. And why that's more efficient is because instead of representing the whole state machine and all possible opcodes at each step, you only pay for the opcode that you use. But the cost of that is that you introduce basically L instances. But as we discussed, instances are constant size. So anyways, there's people experimenting with like all the gray areas between these primitives. The point is like what's your use case and what's going to be efficient for your program.
Does this work for RCS only or would it work for IPv4?
So the question was, does this work for R1CS only? It's a really good question. So I probably don't need to go all the way back, but I committed. Okay, so if you recall, the R1CS was how we chose to represent our NP relation at the very start. And R1CS gave it this very, very nice and simple folding scheme. However, it has its restrictions. So for example, R1CS can only represent degree 2 constraints. Yeah, A times B, quadratic. It can't do higher degree. Do I have 5 minutes left? Okay. Ramon has so few time requirements and I still managed to overrun. So therefore, you might be motivated to fold some more expressive arithmetization. And in fact, people have worked on this. Oh, I deleted those slides, but yeah, basically, people have been trying to fold another popular arithmetization known as Plonk, which supports higher degree gates. sort of an orthogonal line of work is to extend R1CS and to make R1CS more general. And this recent result is called customizable constraint systems, or CCS, that instead of just using the R1CS matrices, uses some linear combination of multi-sets of matrices. And so to answer your question, yes, you can fold different relations, but there are certain, basically for each relation you pick, you need to figure out the details. So how are you going to commit to your witness? And also, what error terms are you going to incur? So before embarking on such a project, you should be very, very convinced that your relation of choice is optimal for your use case. And so in my last 1 minute or something, we promised just now that we could just tack on a ZK snark at the end of the folding. And once again, the reason you want to do this is, first of all, to introduce zero knowledgeness. And then secondly, to avoid the linear time verification and produce instead a succinct proof. I do have the slide showing these efforts to support, to fold different arithmetizations. So for example, Plonk supports higher degree gates. It also supports lookup tables, which come in useful when you want to outsource expensive computations to the pre-processing or offline phase. I think that's all I had. Thank you.
What happens to the size of the group itself? So the whole, for something that's broken down using
The size of the proof. So naively, the proof is linear size for this folding scheme that I've described, and therefore, and we don't like that. Therefore, at the very last step, the prover is gonna put in some effort and make a succinct proof. Basically, to put this linear proof into a ZK snark and compress it down. Yeah.
Is it linear in what?
It's linear in the size of the witness. The proof is the witness,
But it's
basically.
not linear in the number of folding steps?
Oh, it is not linear in the number of folding steps. Yeah, because actually that is the whole point of IVC. Yeah, is that it's constant in the number of steps. Yeah.
Thank you.
Thank you.